So Srikanth will be speaking. This is his final talk of this lecture series, and I guess he'll start talking about Gorenstein rings in local algebra. I think he can start.
Right, so that's a precise description. I know where I'm going to begin. I don't know where I'm going to end. So let me start. So, okay. So let me begin in the local algebra world. I'm supposed to say something about duality and haven't really touched upon it. So let's start in the local algebra context. So for the moment, I'll be looking at the context where R will be a commutative Noetherian local ring. So it might be the ring of functions at some point in a variety. So that's the kind of example you might want to keep in mind, or something like the integers localized at a prime or something. So this is the maximal ideal. M is the maximal ideal. And then K will be the residue field. I already mentioned the definition of a Gorenstein ring last time. So we say R is, the ring R is Gorenstein if, well, let me give you the commutative algebra definition, so to speak. So it's that if you look at all the X groups from K to R, this is just one dimensional and in some degree A. Okay. Now, really, what this is, I'm talking about K, and one is thinking of K as an R module via the canonical surjection. It's really a property of the map R to K. So really, this map is Gorenstein. I say this because eventually you want to replace K with something else. And this then serves as the definition, even in that context. Okay, but I'm getting ahead of myself. So this is the commutative algebra definition of a Gorenstein ring. So what this is saying is that these X groups, right, they're a graded vector space. And what is this as? So this is as a K vector space. So there is, forget the fact that we're in the commutative case, no matter what R is, one is only using the left action here. So there's a right action of K left over, and that gives you a left action on the X group. So this should be as left module, so to speak. Okay. So these structures will become important as we go along, which is why I'm harping on that now. So another way to, before I get on to this, so I should tell you that the reason these are so important is that they come up all over commutative algebra, algebraic geometry. And as you'll see also in other parts of the mathematical world, suitably interpreted. So the key example for would be when R is a regular ring, so something like a polynomial ring in a certain number of variables. But since I'm dealing with the local case, maybe I localize at the variables, or maybe I look at the power series in a certain number of variables. So by the way, when I say local, I'm also assuming the ring is Noetherian. So that's sort of important. So, okay, or any regular ring. Anything of finite global dimension, commutative. So that's one example. Even there's another important class of rings that fits into this called complete intersection. So let me just write it. I don't want to define it if you haven't already seen it. This sections. Then here's another interesting family. So you take, suppose X is a matrix of variables. So Xij. So it's a square matrix of variables. You'll see why it's useful to think of it as arranged in a matrix. So there are, if the matrix has size n, then there are n square variables. Then look at the polynomial ring in these variables. So this is some n square dimensional ring as in Krull dimension, and then factor out the minors of this matrix. So this is the ideal generated by the S cross S minus, size S minus of X. For example, if you, so suppose this was n cross n, then I in X would just be the n cross n minus, and that's just the determinant of X. So this is just one equation, but typically you have more, of course. So this sort of rings define interesting algebraic varieties, and these are all Gorenstein. So there are loads of Gorenstein rings. In fact, if you have not ever looked into this, you might look into a paper of Hyman Bass called the Ubiquity of Gorenstein rings. And there's an updated version, or not updated version, but a commentary on this paper. This is from the 60s, and there's a more recent paper by Craig Hunicke, which talks about some of the subsequent developments about Gorenstein rings. You might take a look at that. Okay, so this is just by way of saying that Gorenstein rings show up all over local algebra and algebraic geometry. And one reason for their interest is their connection to duality. So this finally brings me to what they have to do with duality. So going back to the Gorenstein, so let me go back to the Gorenstein condition. So we had a local ring, and the condition was that this is isomorphic to K as a K vector space, right? As K modules. Let me say K modules, as left K modules even. Now you can rewrite this as the following. So this is saying really, all this is saying is that this is equivalent to this. This is the same data, equivalently in the derived category of K vector spaces. Okay. So because these are just modules, a complex is concentrated in 1 degree, saying that the complexes are quasi-isomorphic is the same as saying their homology modules are the same. Now, I should mention here, by the way, it turns out that A is equal to the Krull dimension, or negative of the Krull dimension of minus of the local ring R. Okay, so this is something special to the local algebra case, that it depends on the Krull dimension. Okay, now there are other modules that have this property that maps into that module turn out to be equal to K. So there's in fact, there is another module. There's another module with this property. Namely the injective hull of K. The injective hull. Okay, so in fact, in this case, so this is by, as the name suggests, this is an injective module, and it's an injective module defined by the condition that this is equivalent to K. And because it's injective, I may as well put this and call this a quasi-isomorphism in D of K. I'll stop writing D of K. So there are two objects which sort of have the same quote unquote, not cohomology, but as far as K is concerned, R and this is true for any local algebra, by the way, not just this holds, this exists for any local ring, right? So for instance, well, maybe I'll get to the example later. So here's an exercise you might do. So RF, any local ring. Okay, then there exists a unique X such that, so this is in D of R. I'm not putting any conditions on X, so it's an R, it's a complex of R modules such that the two conditions. One, that X is K, and two, now as far, when you look at maps from K can't tell the difference between X and its K cellular approximation. So you can't expect uniqueness if you don't also ask that K be K cellular. So X is K cellular, i.e., let me put it for the moment in both languages, local algebra and sort of homotopy theory, that the local cohomology of X is X. Equivalently, this. And last time I explained that these are in this world, cellular approximations correspond to local cohomology functors. Okay, so this is an exercise you can do, and if you're a commutative algebra proof of this would go through the existence of sort of minimal injective resolutions. And it's sort of a fun proof and it's worth doing. All right. So it's saying that this is unique object in the derived category of a local ring with the properties that, this is, I need a language for this, I'll get to it. So that maps from K to X are just K. All right, so what does this all tell you in the world of Gorenstein rings? Thus, when R is Gorenstein, right? Just to sort of belabor the point, we have two things. We have that this is K, where A is, and also the injective, and also we always have, of course, the injective hull. Which is K. So what it tells you is that, so K itself, R itself is not cellular, but this one, okay, so this one is of course the same as for the moment, let me write it in the local algebra language. It's R gamma R. So therefore, we conclude that so it must be the injective hull up to suspension. And in fact, that suspension is really this. Again, let me remind you that A is minus the dimension of R. So this result here is, so this result is what sometimes one might call local duality. So this is Grothendieck's local duality. Suresh already talked about local duality, Grothendieck local duality, and one can prove the version he stated using this this isomorphism here. So it's saying that two objects. So so in the world of topology, well, maybe I'll get to that topology world later. So there are two different objects that in general have no business being the same, but they end up being the same. And maybe I should already allude to something. So what this means is that Therefore, you can look at two functors on the derived category. Functors on the derived category of the ring, and well, coincide on, well, they coincide on K by definition, but they coincide therefore on all finite length objects. On all finite length objects, in fact, on all torsion objects, because every torsion object is a limit of finite length things, on all K torsion or all M torsion or K cellular objects. Equivalently K cellular. I wrote it this way because in some other contexts, this is saying that the Brown Combinates dual is equal to the Spanier Whitehead dual. So this would be something like the Spanier Whitehead dual, where you're looking at maps into the sphere spectrum. And this is the analogous thing in topology would be the Brown Combinates duality. So already you see there are shadows of the topological world appearing here. But before I go there, let me point out that this is connected to say duality. So one can go from here to connect also to say duality that Suresh talked about. And to see the connection, let me rephrase. So using this isomorphism, one can prove the following. So there's a Grothendieck's duality implies that that local, let me just call it local duality, implies that if you take any objects in the derived category, so two conditions. The first condition is that F is a small object, so compact or small. So remember that means the perfect complex. And the second condition, I want to talk about duals, and so one needs some sort of finiteness of cohomology. So no conditions in G, except that maybe I either put a condition on G or I can put a condition on the Hom spaces. Maybe okay, let me put this condition on F itself, so that the length of okay, then there is a duality of this form. So Homs, so this is Homs in the derived category. And check. This is the same as, and so here it is D, which is the dimension of the ring. So it's NG. So where check means, mapping into the injective hull, which is analogous to vector space duality. So I'll get back to that point in a second. Okay, so this, I hope this reminds you of the say duality that you saw for at least vector bundles on projective spaces. So the F being small is like saying F is a vector bundle, and this finiteness hypothesis you need because you're taking duals of some vector spaces. So this is, and from here, I claim this is closely connected with say duality. If you're in the graded context, if R was a graded ring and you applied this to the maximal ideal, so this is like looking at a projective variety and looking at the duality at the affine cone, at the vertex of the affine cone. And so this is closely connected with, let me leave it by saying that this is closely connected with the classical say duality. So there is one feature here that's worth mentioning. In the say duality context, we got the module of higher top differential form. So the canonical module showed up here. It would be F tensor omega or something, the omega D. It just because we're in the local case, that's trivial. So it's just the ring itself, which is why that disappears. But the dualizing module plays an important role in other contexts. Just so happens that in local algebra, it's just trivial, so it doesn't show up. Okay. Now, in fact, this might seem rather restrictive in that you're looking at something small with finite cohomology. Well, the finite cohomology, it's sort of more or less unavoidable because you want to talk about more or less, so you're dualizing something, you want to measure some lengths. But at least you can get around there's a version of this that doesn't ask that it be small. And this is important for some context. So let me just mention it at least in passing. So let's look at the singularity category of the ring. So this is by definition a singularity category of R, which is one description of this is that you're looking at the bounded derived category modulo the small objects, which is the thick subcategory generated by R. Now, so I should mention two names here. It was first considered by Book-White in an unpublished manuscript from the 80s, but it was also rediscovered by Orloff in 2000s. And this is a very important invariant of the ring, the singularity category. And as the name suggests, it's something that would be trivial as if R were non-singular, because then everything is small. So this would be zero. So this might be seen as some measure of the failure of R to be singular. So anyway, when R is Gorenstein, then for all F, so maybe I should change F and say, let's say M and N in dB mod R. And let me state it in a slightly different way. One has a duality. So I'm looking at the maps in the singularity category between M and N. And then you get a similar say duality statement. So it does say that there is say duality on the singularity category. And notice that there'll be N-1 here. And of course, for this to make sense, as long as the length of is finite, because I'm taking duals here with respect to the injective hull. So this is sometimes called Book-White's duality or Auslander duality. Book-White's duality. And as all duality statements, it's really the crucial thing is that there is a pairing. So you can express it as a pairing from, let me see if I can get this right. So if you look at M to N, is saying that some pairing is non-degenerate. So we have the map from here to M to, so we have this just by Anita composition. So this is just Anita composition. And then in some cases, when there is a trace map which takes you to a field. So this is a trace map. And the content of the theorem is that the induced pairing is non-degenerate. And the interesting thing is in this trace map and finding an explicit description of this trace map in concrete situations is a very interesting and non-trivial problem. So Daniel Murphy wrote down this trace map when you're dealing with hypersurfaces. So remember, for example, I said if you look at the determinantal varieties, where you look at a matrix of variables modulo the determinant of the matrix. So that's an example of a hypersurface. So over hypersurfaces, one can give a very explicit description of this trace map. This is tied to the classical theory of residues. And this also has connections to the world of physics, where this is what's called the Kapustin-Lie pairing. So if you want to read any of this, you should look into the work of Daniel Murphy from the 2000s. So that's a very interesting aspect of the story. Unfortunately, I'm not going to get into it. I'd hope to, but it's not going to be possible. The only point I want to make is that this Grothendieck duality, again, just a formal statement of the dual, just the formal statement that there is such a pairing and that's non-degenerate, follows immediately from the Grothendieck's local duality. So on the one hand, this duality theorem gives you say duality, but it also gives you this Auslander-Buchwald's duality for the singularity category of a ring. Yeah, but again, the devil is in the details. So writing down the explicit trace maps is a different story. Okay, so this is all I want to say about connections to local algebra. So let me move on to another aspect. Now, so as I said, you know, where was I? Yeah. So again, we have this. So this was a Gorenstein ring. And as I said, the condition, the Grothendieck duality tells you that this is the injective hull of K up to a shift. Okay. Now, when R is zero dimensional, it is already M cellular, K cellular. So we get that R is the injective hull. R is itself the injective hull. And I claim this is just Poincaré duality. This is saying R is a Poincaré duality algebra. To make this more explicit, so from now on, let me assume that R is actually what is called a supplemented algebra. Is a supplemented K algebra. So we have, that means I have a ring map K to R and K, you know, which would be the case if you're looking at something like KX modulo some homogeneous ideal. So you have K sitting in there and you're mapping onto K. So if you look at it, what happens here is that there's a simple model for the injective hull. So you can look at just this one. So this is an injective R module so this is an injective R module. This is just, you can see by adjunction. And you can also see that again by adjunction, this is just K. So this is just, on K over K, this is just K. So what it tells me is that the injective, you know, so far again, this is nothing to do with Gorenstein. This is true in general. this is the k-cellular approximation of this. I don't even have to derive it because it's already injective. Okay. So this is a general computation for any supplemented algebra, that the injective hull has this concrete description. And really you can interpret this as the space or the module of continuous homomorphisms from R to K, where you give a topology on R, which is defined by the maximal ideal, the emmadic topology on R. Okay. As it be that, as it may, when R is zero dimensional, this is just, in particular, when R is zero dimensional, when R is zero dimensional Gorenstein, I'm going to abbreviate this to Gore. What we get is that isomorphic to this. So this is precisely saying, so here there is, if you're thinking about graded things, you would get a, in the graded word, you would get a twist here. One would get a twist. And let me not write I, but some other invariant. In fact, that's what one would call the A invariant. So let me not confuse matters about something else. If you were in the graded world, you would get an isomorphism like this. But in fact, S would be what Somnath called the dimension, right? The formal dimension of R. It's the class where, it's the degree where there's the R is not, the highest degree where R is non-zero. So you see, it's not so hard to see that, okay, so this isomorphism is supposed to be R linear. And if you unpack what this is saying, it is saying precisely that if you look at the map from here to here, this is non-degenerate. So to sum up, for Artinian rings, the Gorenstein property is precisely saying that the ring has Poincaré duality. So one can view, dimension, dimension 0 for, and our dimension of R is equal to 0. Gorenstein is the same as Poincaré duality algebras. The ring is Gorenstein if and only if it has Poincaré duality. So in this sense, you might think of a higher, sort of the general Gorenstein ring as a higher dimensional analog of a Poincaré duality algebra. So now this brings me to topological considerations. So the topology side of things. Really homotopy theory. So last time around we saw that, yeah?
There is a question in the chat, just quick,
yeah.
I think, what is the significance of writing the isomorphism as a suspension?
So in the graded world, suppose, so if you're dealing in the, so here, when I looked at, if I'm not in the graded world, I can't write down this pairing. All I have is that R is isomorphic dual. But in the graded world, I can unpack it to say that the multiplication is giving me a map from Ri to R, a pairing of this form. And this is actually isomorphic to K. This is one important thing. So S is the top.
Sorry, that's not the question. Why have you written R as isomorphic to S, the suspension of the Hom module? What's
in the graded world?
Huh? Yeah, but what's the complex that you keep?
Yeah, yes, for me, everything, I don't make a distinction between this and this, if that's your question. I'm thinking of R as a DG algebra. Yeah, that's the question.
Fine.
Yeah.
Okay, yeah, okay.
Okay, sorry, Manoj, yes.
Yeah.
And because I'm segueing now into the topological world, and there are no twists, there are only suspensions.
Okay, thanks.
The twist is some, yeah. Sorry, yes. Yeah. So where was I going? Yes, I was trying to say that, last time we saw that in the topological world, we have this notion of Poincaré duality complexes. So Poincaré duality or complexes with Poincaré duality, which are the analogues of Poincaré duality algebras. So for example, orientable manifolds give you such things. And we see now that this lives in the world of Gorenstein rings. And Somnath already defined at least Gorenstein spaces, at least rationally. Which you might think of as corresponding to the topological versions of Gorenstein rings. So already, of course, here there is the duality. Here is the usual duality, the Poincaré duality. Here I told you there is this Grothendieck duality. So you might ask, what is the analog of Grothendieck duality here? And in some sense, I can. So first of all, maybe I should now say that now. So now the context will be. So here's where I get hand wavy, because this is not the time to introduce a lot of machinery. So now we are looking at this, and maybe R is a, so K still will be a field. So R is, K is still a field. Although, as I said earlier on, I alluded to earlier on, it's interesting to allow other coefficients, other things here, ring objects. And R might be a ring or a DG ring or a spectra or whatever. And I don't even want to assume that it's commutative for reasons you'll see later on. And then maybe, if you're in the spectral world, you want to take the Eilenberg-MacLane spectra of K or something like that. So the crucial example for me in the topological side of things would be cochains on BG, which you can interpret as a spectra by looking at maps from the mapping spectra of the classifying space of G into the Eilenberg-MacLane spectra of K. So this would be a crucial example with coefficients in K. So G is a finite group or something more exotic like a compact group. And BG is what's called the classifying space. Or the classifying spectrum, if you want to be in the spectral world. Okay, and the definition is still the same. I don't want to assume that K is characteristic 0 because the cohomology of this is, I'm going to be interested in the modular case where K will be, in this case, the crucial case is when K is FP or where P divides the order of the group. So I don't want to, certainly do not want to just stick to characteristic 0. So this gives me a notion of, so what should Gorenstein mean in this context? So Gorenstein will mean, so R Gorenstein, or I should really be saying R to K Gorenstein. If at this point, I should really be stop writing R hom because it's not the derived or anything, but you should take this in the derived sense. So this is R hom KR. Now, so this is as a caveat to, so this should be in whatever derived sense. Okay, so you're looking at maps from K to R, and you want this to be as some suspension of K. And this should be as K module. So this I talked about before, this object, I'm using up the left R module structures on K and R, but I still have a right R module structure on K that when you dualize becomes a left R module, a K module. So this should be as left K modules. Okay, but there is a lot more structure left in this thing. And there is, in general, you would want one more condition plus one more condition. And you'll see where that condition comes up as we go along. condition, and I'll talk about this in a second, that you can ignore, and that can be ignored when, okay, maybe it's worth saying it here, that can be ignored in the sense that is satisfied automatically. I mean, when K is proxy small, is an R module. And remember, R module should be thought of in the right context. So this proxy smallness, which comes up as sort of a technical condition, seems to be just the right thing that makes a lot of things fall into place. I'll elaborate on this in a second. So this is, forgetting these technicalities, the Gorenstein condition is what you expect. It's just mapped from K to R is this. And then the main theorem under certain conditions, what one proves is that the local duality statement says, then under certain conditions, I would even say a mild condition, under certain conditions, one gets that the cellular approximation, now there's no sense of local cohomology anymore, but I can talk about the K cellular approximation of R. This is isomorphic to this object. Now this still is, one can still form this module. So this is as R modules. Again, you should be interpreted in the right context. One can still form this object here. This is still an R module, and it still has the property that when you look at maps from K to this, you get a copy of K, and it turns out under good. This also presumes that under, so this is implicit that this is K cellular. Whatever conditions I impose, that makes this K cellular. Okay, so this is rather vague, but the main point is to take away from here is that under this Gorenstein hypothesis, you still get an exact analog of the Grothendieck duality theorem in this much greater generality. And these conditions will be satisfied in the local algebra context. So this is truly an extension of the Grothendieck local duality. Now, this one is interesting because what one is interested, so again, this leads to a spectral sequence. Relating, okay, now assuming that the R is sufficiently commutative. So if you look at the homotopy groups of R, you can then look at the usual local cohomology. So this will be some commutative ring. You can look at the usual local cohomology of these things, of this as a ring, and this will converge to the homotopy groups of this, the dual here, which will be the dual of this. So I hope you begin to see that it's saying that ignoring this factor of local cohomology, it's saying that there is some connection between the homotopy of R and its dual. So this is once again Poincaré duality is coming up here. This is some extension of Poincaré duality. And this is an extension of Poincaré duality. So all this works applies when you're looking at cochains on BG and K is FP. And although one can push this a bit further, let me assume that G is a P group. So P is, and P divides the order of the group, of course, otherwise, yeah. So, you know, the order of G is some power of P. Then what we get is a spectral sequence. We get that this is Gorenstein, or you don't have to take FP, any field of characteristic P would do, but let me stick to FP. This is Gorenstein. And we get a what's called a local cohomology spectral sequence going from the local cohomology of the cohomology of this ring, which is group cohomology, converging to, well, it turns out here the suspension is it -1? I think it's -1. To group homology. So this is group homology here, which is just a dual of group homology. And this is group cohomology. So we get a spectral sequence, and this goes by the name Benson-Carlson duality. So it would be meaningless for me to sort of try and jump into the technical details of this. So this does have applications to computing the Poincaré, the Hilbert series of the cohomology, the group cohomology of a finite group. Okay, it tells you, for example, let me just throw it out there for people who know this. It just says, it implies that when the cohomology is Cohen-Macaulay, it's actually Gorenstein. It's talking, it must be Gorenstein as a graded ring. And that has implications to computing the Hilbert series of this graded ring. So it's saying something special about the cohomology rings of finite groups. Okay, so this version of Poincaré duality for Gorenstein algebras and this generality gives you recovers Benson-Carlson duality on this side. Now, in the last few minutes, what I want to do is go back to try and convey some idea about what is involved in going from this condition as left K modules to the statement that this is equal to hom K R K. So what goes into this? So the ingredients of this. Okay, so remember, I left this as an exercise in the local algebra context where one can do the exercise using minimal injective resolutions and things like that. I want to try and give a homotopy theoretic proof of this. And that proof goes as follows. So, you know, this one, this actually is naturally a left E module, sorry, a right E module. Where E, there's no need to write script. Where E is the endomorphisms of K. So this came up when we talked about Dwyer-Greenlee's correspondence. Of course, the derived endomorphisms. So this has naturally a right E module structure because K, K is a left E module and the R action is compatible with that. So that's left over and you get a right E module structure. But now via this isomorphism, this means that K acquires a right E module structure, which is something new. So we get right E action on K compatible with its left one. So that means K becomes a bimodule over E. This is a new piece of structure. Okay, and what one wants to say is that, so there is also another structure. There is also a structure. There is a right E structure coming from this isomorphism. If you look at maps from okay, so basically, you have two, again, you should this should remind you of what I brought up before, that there are two modules, in this case R itself on the one hand, and now this is the K dual of R. They both are giving you right E actions on K. And one of the things that one has to prove is that under certain, when R, under certain hypothesis, when R is proxy small, when K is proxy small over K, when K is proxy small as an R module, one can prove that the right E actions all coincide on K using arguments similar to those that go into the proof of the Dwyer-Greenlee's result. Coincide. So this is one of the miraculous things for me anyway about this proxy smallness condition. So what we get is that yes, this is equivalent to, sorry. So it tells me that this is equivalent to this as E modules, right E modules. But then this implies that, so this sort of, it's alluding to what one of the crucial points is to understand right E actions on K that are compatible with the left actions. So it's something to do with, it's an orientability issue, and it may come up, and I'll tell you in one specific example, and you'll begin to see this. And then I'll wrap up, by the way, in a minute. I know I'm close to time, or maybe over time. So this tells me that when I tensor with K, over E, this is as right as now as left R modules. Okay, and this is nothing. I'm just saying we have an isomorphism as E module. So when you base change or you tensor with K, you have the isomorphism as R modules. But then the Dwyer-Greenlee's theorem tell you that because K was proxy small, this is the same as the cellular approximation of this. And this is the same as a cellular approximation of R. So you see that these two end up being the same. These two end up being the same. And under certain connectivity hypotheses, this ends up being, so under suitable connectivity hypothesis on R. This ends up being already K cellular. So this is analogous to what I said before, that if you look at the graded case, R was a graded ring, say connective graded ring with K in degree 0, then this was already K-cellular or co-connective and simply connected or something like that. Okay, so at the end of the day, it's just this Dwyer-Greenlee's correspondence plus the analysis of E, the right E actions on this object. So one last thing I want to say, so going back to this example, when you look at R to be co-chains on BG, if you look at what end is, so this is looking at endomorphisms of, the topologists would know this computation easily. Either it's the Eilenberg-Moore or the Rothenberg-Steenrod computation. So this is the same as chains on loops on BG, which is the group algebra of G. So because P is a P group, so because when G is a P group, so now in this case, when you're looking at the right actions of G, of the right module structures of G on K, you're looking at characters. And when G is a P group, there are no characters. So this is why the K has only the trivial module structure. So that's what I alluded to when I said it's an orientability issue. The right K actions on, right E actions on K. So you see it very clearly in this one example. And so this is one thing I wanted to mention. So in the last 1 minute, let me just talk through this. So this is explaining why BG begins to fit in this. So I should also maybe mention two other facts that make it easy to recognize that C star, this cochains on BG, is a Gorenstein algebra. So R to K is proxy small. So how do you prove that something is proxy small? Well, in general, it's a bit hard, but under these, this is if and only if E to K is proxy small. So proxy smallness is Morita invariant. So I have to explain how there's a map from E to K, but this is sort of standard. It comes from the augmentation. So we're in the augmented world, remember? So this tells me that E also there's a map from E to K. So this is proxy small if and only if this is proxy small. And in this one example, this is asking that K is proxy small as a KG module. But that, KG itself has a finite filtration by K modules. So K builds this free module, and that shows that this is proxy small. The other thing, and this is sort of something like Koszul duality, is that R to K is Gorenstein if and only if E to K is Gorenstein. And this tells you that C star, it's classical that the group algebra is Gorenstein. So for example, KG is Gorenstein. So this implies that C star BG is Gorenstein. So this is because it's a self-injective algebra. In the world of algebras, it's a zero-dimensional Gorenstein ring, the group algebra for finite group. So it tells me, all this machinery then tells me that cochains on BG is Gorenstein. So this is how one proves that these things are Gorenstein. There's a lot more to the story here. One can ask about the Gorenstein property and how it behaves under fibrations and so on, but that's for another day. I'll stop here.